What happens when something coming from the darkest depths of the universe begins to behave in ways that no scientist on Earth expected? Tonight, friends, stay until the end, because what is happening in our sky could forever change the way we understand the cosmos. Just a few weeks ago, a telescope located in the heart of Mexico City captured something extraordinary, something that has astronomers around the world awake at night, searching for answers that seem to slip through their fingers like fine sand. Good evening, dear listeners. Felipe Suarez here, accompanying you on this starry night. Have you ever thrown a stone into the air and expected it to change course on its own? Because that, in essence, is what we are witnessing with this cosmic visitor called 3I Atlas. And I know it sounds impossible. I know it seems like something out of a science fiction movie, but the data is there. The images do not lie. What will happen when this object reaches the vicinity of Jupiter in 3 years? Join me to find out. The comet 3I Atlas is not an ordinary visitor. It was not born in our solar system. It did not form in the Oort cloud or in the Kuiper belt, those frozen regions that harbor the comets we have known for centuries. This object traveled distances that the human mind can barely conceive, crossing the void between the stars for millions, perhaps billions of years, until it finally arrived in our cosmic neighborhood. And from the moment it was first detected, it began to show behaviors that defy everything we thought we knew about comets and about the laws that govern the movement of celestial bodies. The most recent images captured by a team of astronomers working tirelessly in Mexico City revealed something that left the scientific community in a state close to amazement, mixed with a deep unease that few dare to admit publicly. The trajectory of this comet, according to the most precise calculations available, experienced an adjustment. Not a chaotic deviation caused by random forces, not a casual push from the solar wind as happens with so many other objects that cross through space. It was a precise change, almost millimetric in astronomical terms, that placed it on a direct encounter route with Jupiter's Hill radius. To understand the magnitude of this finding, one must first understand what exactly the Hill radius is. Imagine an invisible zone around any massive planet, a subtle frontier where the gravity of that world begins to dominate over that of the Sun. It is like a territory of its own, a gravitational realm that separates a planet's influence from the influence of our parent star. Jupiter, being the undisputed giant of our system, possesses an enormous Hill radius that extends for more than 53 million kilometers in all directions. It is a region of space so vast that it could contain Earth hundreds of times without the slightest problem. And 3I Atlas, after that mysterious adjustment in its trajectory, is heading exactly toward that edge. Not near it, not in its general proximity, but exactly toward it. The precision is the type that makes astronomers stop what they are doing, review their calculations 2 and 3 times, and then look for errors that simply are not there. It is the type of precision that defies statistical probabilities in a way that is profoundly uncomfortable for those who prefer simple and conventional explanations. But here comes the part that truly keeps those who study these phenomena with dedication and rigor awake at night. That adjustment did not occur when we could observe it. It happened when the comet was behind the Sun, completely invisible from Earth, beyond the reach of any terrestrial or space telescope. It was as if the universe had decided to deliberately hide the exact moment when something extraordinary happened. When the object finally reappeared in our field of vision and scientists updated their orbital models with the new data, they discovered that something, whatever it may have been, had pushed the comet just enough to change its destiny radically. The probability of this happening by pure chance is astronomically low. We are talking about 1 in a billion, perhaps worse. It is like throwing a dart from 100 meters away blindfolded in the middle of a windstorm and still hitting right in the center of the target. That is exactly what this interstellar visitor has just accomplished, and no one can explain how it did it. The telescope that captured these observations does not belong to any multinational space agency or to a government observatory with million-dollar budgets. It is an instrument operated by Mexican amateur astronomers who dedicate their nights to scrutinizing the sky with a passion that rivals that of any professional. These observers, armed with equipment they themselves have configured and calibrated during years of meticulous practice, manage to detect subtle changes in the comet's position that the automated systems of other institutions overlooked. The importance of this discovery lies not only in the phenomenon observed, but in who observed it and how they did it. It demonstrates that citizen astronomy, that tradition of looking upward with genuine curiosity, remains a vital force in the exploration of the cosmos. Do you realize what this means, my friends? We thought a comet was simply a ball of ice drifting along, following the laws of gravity like any other object in space. But 3i Atlas is telling us that maybe it is not that simple. What kind of natural force can produce that level of precision? There is something we are not seeing, something our instruments cannot detect yet. I promise you that the further we advance in this story, the more fascinating it gets. When a celestial object changes course unexpectedly, scientists look for explanations within the framework of known physics. It is the natural procedure, the path that science has traveled for centuries to understand the mysteries of the universe. The first candidate, the most obvious and studied, is outgassing. Comets are composed mainly of ice, dust, and volatile compounds that sublimate when they approach the Sun. Those jets of gas act like small rocket engines, pushing the comet in directions that may seem unpredictable, but that follow identifiable patterns when analyzed in sufficient detail. It is a well-documented phenomenon, observed in dozens of comets over decades of meticulous study. Astronomers have developed sophisticated mathematical models that can predict with reasonable accuracy how outgassing will affect the trajectory of a given comet. But here is the fundamental problem with that explanation when we try to apply it to 3i Atlas. Outgassing produces chaotic pushes, not precise adjustments. It is like trying to park a car by blowing at it with an industrial fan. You could move it, no doubt, but you would never place it perfectly in the designated space, aligned to the millimeter with the lines painted on the ground. And yet, that is exactly what seems to have happened with 3i Atlas. The push was of the exact magnitude, at the exact moment, to place it on a trajectory that will culminate in March of the year 2026 with a close encounter at Jupiter's gravitational limit. It is the type of coincidence that makes even the most skeptical scientists begin to scratch their heads with genuine perplexity, searching for alternative explanations that simply do not appear. The Mexican team that made the initial observations worked for weeks, processing the collected data. Each image was analyzed with specialized software that allows measuring positions with a precision of fractions of an arc-second. Each measurement was compared with the ephemerides published by the Minor Planet Center, the world authority on tracking solar system objects. The discrepancies they found were not calibration errors or artifacts of digital processing. They were real differences between where the comet should be according to previous orbital models and where it actually was in the night sky. At first, the observers thought they had made some mistake. They reviewed their procedures, recalibrated their instruments, consulted with colleagues from other countries who were also following the object. But the results were confirmed again and again. The comet had changed course, and no one could explain why. The images captured from Mexico City also reveal another intriguing element, something that adds an additional layer of mystery to this cosmic enigma that grows with each new observation. 3i Atlas not only changed its course inexplicably, it is also exhibiting a completely anomalous tail structure that defies the models established during decades of cometary research. Comets, as many know, develop spectacular tails when they approach the sun's solar radiation and stellar wind push dust and gas away from the nucleus, creating those luminous trails that have fascinated humanity since time immemorial. Our ancestors saw them as omens, as divine messages written in the night sky. Today we know they are perfectly natural physical phenomena, the result of the interaction between cometary material and the energy of our star. But 3i Atlas has something that very few comets show, something that has puzzled observers since the first weeks of intensive tracking. An anti-tail, a tail that points toward the sun, not away from it. This phenomenon, although rare, is not completely unknown in cometary astronomy. It occurs when heavy particles remain suspended along the comet's orbit, and from a certain observation angle appear to form a tail that defies apparent logic. It is a perspective effect, nothing more. Or at least that is what it should be according to all the models we have developed. But here comes what truly has me fascinated, friends. The anti-tail of 3I Atlas is too narrow, too defined, too stable. Do you know what it looks like? It looks as if someone had traced a straight line with a laser through millions of kilometers of empty space. And that, according to the physical models we have, simply should not be possible. Are you beginning to understand why this object has everyone so unsettled? When a comet releases dust into space, that dust should disperse in a predictable manner. The sun's gravity, the constant pressure of solar radiation, the small gravitational perturbations caused by nearby and distant planets. Everything contributes to the particles spreading in a broad and diffuse pattern over time. It is basic physics, celestial mechanics that we have understood and used to predict the behavior of countless objects for more than 3 centuries of rigorous astronomical observation. But the anti-tail of 3I Atlas does not behave that way. It looks orderly, it looks intentional, it looks as if something were keeping those particles in perfect formation across distances that defy human imagination. And that raises a profoundly uncomfortable question for the scientific community. A question that many prefer to avoid, but that becomes inevitable when the data is analyzed honestly. Astronomers have proposed several theories to try to explain this anomaly, working day and night to find answers that satisfy the demands of the scientific method. Perhaps the composition of the comet is completely unusual, with types of ice that sublimate in ways our models do not yet capture correctly. Perhaps magnetic fields are involved, electromagnetic interactions between cometary dust and solar wind that our equations still do not describe with sufficient precision. Perhaps the internal structure of the nucleus is so irregular, so different from any comet we have studied before, that it produces perfectly directed gas jets, which create apparently artificial patterns, but which in reality obey natural processes that we simply do not understand yet. All of those are possible explanations. Scientists are working with every available piece of data, every captured image, every spectroscopic measurement. But here is the fundamental problem that none of these theories can completely solve. None of those explanations fits perfectly with all the observations. Every time a theory seems to work to explain one aspect of the behavior of 3I Atlas, a new detail appears that does not fit, a piece of the puzzle that simply does not match the rest of the picture. Observations made in recent weeks have revealed significant changes in the color of the coma surrounding the comet's nucleus. Before perihelion, that point of closest approach to the Sun, the coma showed a characteristic reddish hue. But approximately 4 weeks after perihelion, images obtained by a large telescope 8 meters in diameter began to show the halo with a distinctive green coloration. This color change is not a minor detail or an unimportant curiosity. The green tone is a strong indicator of the presence of molecules such as diatomic carbon, which emits light in that specific range of the electromagnetic spectrum. In practical terms, this means that the molecular composition of the coma changed after passing through the intense heat near our parent star. This type of change implies chemical and dynamic processes occurring at scales that still need to be measured and fully understood. Diatomic carbon is a molecule that forms when more complex organic compounds disintegrate under intense solar radiation. Its presence indicates that the comet's nucleus contains carbon-rich materials, possibly complex hydrocarbons, or even prebiotic compounds that could be relevant to our understanding of the origin of life in the universe. Spectroscopists are analyzing every photon of light arriving from the comet, breaking down its spectrum into thousands of individual lines that act as chemical fingerprints. Each line corresponds to a specific energy transition in some atom or molecule, revealing the composition of the material emitting that light. What they are finding is fascinating and puzzling in equal measure. The proportion of certain elements does not match what we would expect from a comet formed in our solar system. The relative abundances of carbon, nitrogen, and oxygen suggest an origin in an environment very different from the one that gave rise to our Sun and its planets. Had you ever thought that a comet could change color like that, as if it were a cosmic chameleon? Neither had I. And there is something else that does not let me sleep peacefully. Space instruments sensitive to X-rays detected a glow coming from the region around 3I Atlas. The extent and spatial distribution of that emission are greater than expected for a typical comet with similar visual appearance. What is really happening up there, friends? Another relevant point that has captured the attention of the most meticulous researchers is the X-ray emission associated with the interaction with the solar wind. Space instruments sensitive to this wavelength observed brightness coming from the region around 3I Atlas. The most plausible mechanism, already studied in other comets, involves the interaction between the solar wind and the gases released by the coma, which generates emission in this particular energy range. What stands out here is not simply the existence of X-rays, something that has been observed in other comets before, but the observed extent of this glow. According to data published by various research teams, the reach and spatial distribution of the X-ray emission are considerably greater than expected for a typical comet with similar visual appearance. It is as if the object were radiating energy at scales that exceed the predictions of our current models. The solar wind is a constant stream of charged particles emanating from the Sun's corona at speeds of hundreds of kilometers per second. When these particles collide with atoms and molecules in a comet's coma, they can strip electrons from those atoms in a process called charge exchange. The solar ions, now neutralized and in excited states, release their excess energy by emitting X-ray photons. It is a well-understood process that occurs in all comets that approach close enough to the Sun. But the amount of X-rays that 3I Atlas is producing suggests that there is something unusual in the interaction. Perhaps the composition of the cometary gas is different, with chemical species that produce more intense emissions. Perhaps the geometry of the coma is such that it maximizes the efficiency of the process. Or perhaps something completely different is happening, something our current models do not contemplate. There is also the matter of visual scale. Recent images cover enormous regions around 3I Atlas, spanning from hundreds of thousands to millions of kilometers. This provides an important physical context that should not be overlooked. The observed structures are not local details or small irregularities that could be attributed to photographic effects or data processing. They are massive features occupying volumes comparable to the largest interplanetary systems we know. When we talk about plumes and jets extending millions of kilometers into space, we are not dealing with small surface variations. We are facing phenomena that require considerable sources of energy and mass, sources that our current models have difficulty explaining satisfactorily. The distribution of dust around 3I Atlas presents another mystery that has perplexed the most experienced specialists. In a typical comet, we expect to see a clear separation between fine particles and coarse particles. Fine dust, being light, is quickly pushed far from the nucleus by the pressure of solar radiation. Coarse dust, being heavier, remains closer to the original orbital trajectory. Over time, this separation becomes very evident in observations, allowing astronomers to clearly distinguish between different types of material. But in 3I Atlas, this separation is not as clear as it should be. There are regions where fine dust and coarse dust appear mixed homogeneously, as if they had been released at the same time from the same region of the nucleus, but then behaved in completely different ways than expected. It is a pattern that defies our models of cometary dust emission in fundamental ways, forcing researchers to rethink assumptions they had taken for granted for decades. The polarimetry technique, which measures how light reflected by cometary dust is oriented in space, has revealed another significant anomaly. The polarization values observed in 3I Atlas are strongly negative, which is extremely rare in known comets. Negative polarization indicates that the dust particles have optical properties very different from normal. They could be more porous, more irregular in shape, or composed of materials with unusual refractive indices. Some researchers have suggested that the dust from 3I Atlas could contain significant amounts of complex organic material, which would explain both its anomalous optical behavior and the carbon enrichment detected spectroscopically. And when I say it does not fit, my friends, I am not talking about small discrepancies that we can adjust with a bit of advanced mathematics. I am talking about differences that force us to reconsider our most basic assumptions about how these objects work. Could 3I Atlas be made of materials we have never seen before? Does it come from an environment so different from ours that its physical processes bear no resemblance to what we know? Think about it for a moment. That possibility is very real and deserves serious consideration by the entire international scientific community. 3I Atlas is an interstellar object, which means it formed somewhere completely outside our solar system, perhaps around a star very different from the Sun, a cold red dwarf whose light barely warms the planets orbiting it, or a blazing blue giant whose intense radiation creates conditions that do not exist anywhere in our cosmic neighborhood. Perhaps it formed in a region of the galaxy where the conditions of temperature, pressure, and chemical composition were radically different from those that existed in the primordial nebula that gave rise to our own solar system approximately 4,500,000,000 years ago. If that is the case, then the comet could contain types of ice that we have never had the opportunity to study directly. Organic compounds that do not exist on Earth or in any local asteroid or comet. Crystalline structures that sublimate in completely unexpected ways when heated by the light of our star. All of that could explain, at least in part, why the behavior of 3I Atlas is so puzzling for our current models. But even accepting those extraordinary possibilities, the problem of precision still remains. We still have to explain how a supposedly natural object could adjust its trajectory with such exactness that it will end up passing through Jupiter's Hill radius in the year 2026. And that, honestly, is the hardest part to accept. Not because it is physically impossible, but because it requires such a specific, statistically improbable combination of factors that it almost seems designed by some intelligence capable of calculating trajectories across distances and times that exceed anything humans have ever attempted. Jupiter's Hill radius is an immense region of space with a radius of more than 53 million kilometers. It is a zone where the giant planet's gravity begins to dominate over the Sun's gravitational influence. For an object traveling through interstellar space at tremendous speeds, arriving exactly at that edge has no obvious purpose from a purely physical point of view. It is not a place where anything special happens naturally, like a tidal breakup or a sudden thermal activation. It is not an orbital resonance point that could capture the object and turn it into a new permanent member of our system. It is simply a gravitational boundary, an invisible frontier in the void of space. And yet, 3I Atlas is heading directly toward it with a precision that is almost disturbing for those who analyze the data carefully. Orbital calculations show that the comet will cross Jupiter's gravitational sphere of influence at a specific moment, when the giant planet will be in a particular position in its 12-year orbit around the Sun. If the trajectory had been slightly different, if the observed adjustment had not occurred with the exact magnitude it had, the comet would have passed at a considerable distance from Jupiter, without any significant interaction with its gravitational field. But with the adjustment that occurred, the encounter will be close. Not close enough for the comet to be captured or destroyed, but close enough for its future trajectory to be substantially modified by Jovian gravity. It is what space engineers call a gravitational assist, the same technique we use to send our probes to the edges of the solar system. I constantly wonder, friends, if this were a coincidence, it would be one of the most extraordinary coincidences in all of modern astronomical history. But if it is not a coincidence, if there is a reason why this interstellar visitor is heading toward that specific point in space, then we have to ask ourselves, what is that reason? Is there something at Jupiter's Hill radius that we are not seeing? Something our instruments do not detect? The possibility that the comet's trajectory was determined long ago, perhaps even before it entered our solar system, is speculative, no doubt, but it is not completely far-fetched when considered within the appropriate context and with the open mind that genuine science requires. If 3I Atlas were an artificial object, or at least an object whose movement had been influenced by some type of technology at some point during its long journey through interstellar space, then its trajectory could have been planned in advance. It could have been designed specifically to perform a flyby of Jupiter, perhaps to use the planet's immense gravity as a gravitational boost, a cosmic slingshot that would accelerate it on its way out of the solar system toward a new destination among the distant stars. It is a maneuver that our own spacecraft have performed dozens of times with resounding success. Voyager 1 and Voyager 2, those ambassadors of humanity now navigating through interstellar space carrying messages from our world to whoever might find them someday, used Jupiter precisely for that purpose more than 4 decades ago. And if an extraterrestrial civilization wanted to send an exploration probe across the galaxy, using giant planets like Jupiter to adjust trajectories and gain speed would be a perfectly logical and extremely energy-efficient strategy. Professor Abraham Loeb of Harvard University is one of the most prominent voices, and also one of the most controversial, in this type of debate that mixes rigorous astronomy with questions many would prefer to avoid. He is not a marginal theorist or a media attention seeker chasing sensationalist headlines. He is a genuinely respected scientist with hundreds of publications in the world's most prestigious scientific journals. Someone who led Harvard's astronomy department for almost a full decade, and he has suggested something that makes many of his colleagues feel profoundly uncomfortable. Loeb argues that objects like 3I Atlas, and before it the famous Oumuamua, might not be completely natural in their origin or in their current behavior. He is not categorically stating that they are alien spacecraft. He is not saying that there are beings from other worlds piloting them through the cosmos. What he is saying with the caution proper to a rigorous scientist is that the anomalies we are observing are so significant, so difficult to explain satisfactorily with known physics, that it would be scientifically irresponsible not to consider all possibilities. And that includes, however remote the probability may seem, the possibility that we are observing something out of the ordinary. Something that could include technology of unknown origin. Oumuamua was the first of these visitors to be detected. It appeared without warning in October of the year 2017, captured by the Pan-STARRS telescope located in the volcanic heights of Hawaii. Its name in the Hawaiian language means approximately messenger from afar arriving first. And it was a truly strange messenger, without the slightest doubt. Its shape was completely unusual for any known cosmic object, elongated like a giant cigar, perhaps 10 times longer than wide, a proportion that had never been observed in any asteroid or comet in our solar system. It showed no visible tail despite having passed relatively close to the Sun, something unexpected if it really was a traditional comet with ices that should have evaporated under solar heat. And most puzzling of all, it accelerated as it moved away from our star, as if something invisible were pushing it outward. Astronomers proposed multiple explanations for that anomalous behavior. Outgassing of exotic ices that did not produce a visible tail, solar radiation pressure acting on an unusually reflective and thin surface, complex thermal effects that no one had previously considered. But no explanation fit perfectly with all the available observations. Each theory left some loose end, some unresolved detail that troubled the most meticulous researchers. And then, before we could study it more thoroughly with more powerful instruments, Oumuamua disappeared into the darkness of interstellar space, moving away from us at tremendous speeds, leaving us with more questions than answers and a persistent feeling of lost opportunity that still pains those who dedicated entire weeks to trying to understand its nature. Look, friends, I know perfectly well that sounds like science fiction, I know. But if Loeb is asking these questions from Harvard's chair, and more scientists are beginning to admit, even if only in private conversations, that there is something genuinely strange about these interstellar visitors, then perhaps we too should keep an open mind, do you not think? Do you remember Oumuamua? And now we have 3I Atlas, another interstellar visitor, another object that behaves in ways that defy our established expectations. And this time the situation is different. This time the object is not leaving yet. This time we have years ahead to study it, to observe it with every available instrument, to try to truly understand what is happening. Loeb and his collaborators have approached the most recent data from 3 main lines of reasoning that deserve careful consideration. The first concerns the change in composition. The transition from red to green is consistent with the activation of different molecules near our parent star, especially with the presence of diatomic carbon in the period after perihelion. This indicates that the coma contains variable components, and that heating significantly alters the chemistry of the observed emission. It is evidence of complex dynamic processes occurring in real time as the comet navigates through the inner regions of our solar system. The second line involves X-rays and their anomalous extent. While X-ray emission is expected when there is interaction with the solar wind, the observed intensity and extent raise important questions that do not have easy answers. The central problem is that the amount of gas required and its spatial distribution seem incompatible with the estimated size of the nucleus. If we assume conventional cometary behavior, the numbers simply do not add up. A nucleus of the estimated size for 3I Atlas should produce a coma of a certain size and density. But the observed coma is larger and more active than those estimates predict. It is as if the comet were releasing more material than should be physically possible given its apparent size. The third line deals with the real and persistent anti-tail. The anti-tail of 3I Atlas cannot be attributed to a simple geometric perspective effect. Images obtained over time show that it points consistently toward the Sun at different times and from different positions of Earth. For Loeb, this demands direct physical explanations, whether through fragments of ice released from the side facing the star or through collective dynamics caused by non-gravitational acceleration. In comets from our system, the presence of an anti-tail can usually be explained by a geometric projection effect when Earth crosses the comet's orbital plane. In the case of 3I Atlas, the anti-tail appears in images obtained under geometric configurations in which this effect can be safely ruled out. This means we are not dealing with an optical illusion, but with real emission toward our parent star. The paradox arises because basic dust and gas physics predicts that both radiation and solar wind push particles away from the star. Thus, observing a luminous plume directed toward the star requires an explanation that goes beyond the standard understanding we have developed during decades of rigorous cometary study. Among the possibilities scientists are considering are the massive release of extremely small fragments that evaporate rapidly before being pushed away, or the existence of a localized dynamic flow that actively directs material toward the star. It has also been proposed that a swarm of objects or particles could lag behind the main trajectory due to non-gravitational acceleration of the main body, creating a collective effect that manifests as a plume directed toward the star. Another hypothesis involves complex sublimation processes with atypical composition, dominated by gases such as carbon monoxide and carbon dioxide with little water, altering the dynamic response of particles to solar radiation in ways we have not observed before. Each of these hypotheses solves part of the problem, but none manages to simultaneously explain the color change, the X-ray emission, the observed scale, and the persistence of the anti-tail without resorting to assumptions that are still poorly tested. This is exactly the point emphasized by Loeb. Recognizing the anomaly is the first step toward advancing scientific knowledge. Will there be enough time to solve the mystery, friends? Or will it leave us with even more questions than we already have? The truth is that no one can know for certain at this moment, but what we do know is that every day that passes, every new image captured, every new measurement made, brings us a little closer to the truth. and that, in itself, is already extraordinary. Does it not seem exciting to you to be witnesses to this? The images obtained from the telescope in Mexico City are contributing crucially to this international scientific effort. The clarity of the photographs, the resolution achieved, the ability to capture fine details in the tails and in the enigmatic anti-tail. All of that is allowing researchers around the world to build an increasingly complete model of what is really happening with this cosmic visitor. And what they are observing is absolutely fascinating. The tails of 3I Atlas are not static structures, as might be expected from a simple chunk of ice and rock drifting along. They are constantly evolving, changing shape, developing new structures almost in real time before the astonished eyes of observers. There are specific moments when the anti-tail intensifies dramatically, becoming brighter and more defined than any model predicts. There are moments when new secondary tails seem to sprout from the nucleus like branches of a cosmic tree, growing at impossible speeds. It is as if the comet were somehow alive, breathing, reacting to changing conditions as it travels through our solar system toward its encounter with Jupiter. Normal comets, of course, also show changes in their activity over time. But generally those changes are predictable, clearly correlated with distance to the Sun, with the rotation of the nucleus on its own axis, with the orbital geometry that determines how much solar radiation they receive at any given moment. They are changes that our models can anticipate with reasonable precision based on decades of observation and analysis. With 3I Atlas, the changes seem to occur without a clear reason or an identifiable pattern. It is as if the comet were responding to signals we cannot detect with our current instruments, reacting to invisible stimuli that escape our present understanding. One of the aspects that has generated the most intrigue in the scientific community is the variability of the object's brightness. Astronomers are documenting fluctuations that do not correlate cleanly with the expected rotation of the cometary nucleus. The light curve, that record of how brightness changes over time, shows irregularities that suggest an extremely complex shape of the nucleus or emission processes that vary in ways our current models cannot satisfactorily reproduce. High-precision photometry, performed both from professional observatories and by dedicated amateurs, reveals that the comet experiences sudden increases in brightness followed by equally rapid decreases. These bursts of activity do not always coincide with moments when the nucleus should be showing its most active regions toward the Sun. It is as if activity arose spontaneously, driven by internal processes we do not understand. Some researchers have suggested that the nucleus could be fragmenting, releasing pieces that rapidly sublimate and produce the observed brightness increases. But there is no clear evidence of secondary fragments in the images, as has been observed in other comets that have disintegrated before our eyes. The public reaction to these discoveries has been immediate and intense. In live broadcasts and on social media, severe criticism has emerged toward the agencies that published the images. Some people even accused the official images of manipulation or charlatanism. There has also been distrust regarding the successive adjustments of orbital parameters published by official bodies. Among the most repeated points in the public debate are issues that deserve scientific attention rather than polarization. One of them is the difference between raw data and processed images, since adjustments in contrast, filters, and mosaics can alter the perception of color and the extent of the observed structures. Another point is the successive corrections of orbital parameters, which are normal, but should be accompanied by clear documentation of methods and uncertainties. There are also disputes about composition, with observers pointing out that some reports avoid direct statements about certain elements, limiting themselves to interpretations, which generates distrust when the data is not open and accessible for independent verification. It is as if 3I Atlas were playing with us, friends, revealing clues here and there, but never showing the complete picture. And that is precisely the frustrating, but also fascinating part of all this. Every time we think we are close to a definitive answer, a new piece of data appears that complicates everything. Will we ever fully understand it? That is what we all wonder every night looking at the stars. Over the coming weeks and months, more data will continue arriving from observatories around the world. More analyses will be published in scientific journals. More researchers will offer their interpretations of what is really happening up there. The Mexican telescope that made the first crucial observations will continue monitoring the interstellar visitor. Its operators, those passionate amateurs who dedicate their nights to scrutinizing the cosmos, are now in contact with international networks of observers coordinating follow-up campaigns. Every clear night is an opportunity to capture new images, to measure new positions, to detect changes in the comet's activity that could reveal clues about its true nature. Citizen astronomy, that tradition of collaboration between professionals and amateurs, is once again demonstrating its invaluable worth. When large space telescopes cannot observe an object because it is too close to the sun in the sky, it is the small terrestrial telescopes that fill the gap. When automated systems overlook subtle changes in position or brightness, it is trained human eyes that detect the anomalies. And when the scientific community faces a mystery that defies all conventional explanations, it is curious minds from around the world, professionals and amateurs alike, who work together to unravel the truth. 3i Atlas continues its silent journey through our solar system. Each day it comes a little closer to its appointment with Jupiter, that date marked on astronomical calendars around the world, March of the year 2026. No one knows for certain what will happen when the comet crosses the Hill radius of the giant planet. Perhaps its trajectory will be deflected toward outer space, sending it back to the interstellar depths from which it came. Perhaps the gravitational interaction will reveal new information about the mass and density of the nucleus, data that could help solve some of the mysteries that currently puzzle us. Or perhaps something completely unexpected will happen, something no one has predicted, something that once again defies our expectations and forces us to rethink what we thought we knew. The only certainty is that we will be watching. Telescopes from around the world, large and small, professional and amateur, space-based and ground-based, all will be pointing toward that point in the sky where a visitor from the stars meets the king of the planets. And perhaps, just perhaps, in that encounter we will find the answers we have been seeking since we first looked up at the night sky and wondered what else is out there. The universe is vast, vaster than we can imagine, and it is full of wonders we are only beginning to discover. 3i Atlas is just one of them, a reminder that no matter how much we have learned in centuries of scientific exploration, there is still infinitely more to know. Each generation of sky observers has found something that changed our understanding of the cosmos. Galileo saw Jupiter's moons and knew that not everything revolved around Earth. Hubble measured the distance to galaxies and discovered that the universe was inconceivably larger than anyone had imagined. Modern astronomers detected planets orbiting other stars and confirmed that solar systems are common in the galaxy. Now, perhaps, we are on the threshold of another transformative discovery. An object from the depths of interstellar space that behaves in ways that do not fit any existing model. A visitor that raises questions as old as humanity itself. Are we alone in the universe? Are there other beings out there, looking toward the stars with the same curiosity as us? And if one of them decided to send a message, how would we know to recognize it? Perhaps 3i Atlas is simply a very unusual comet, a product of physical and chemical conditions that do not exist in our solar system. Perhaps all its anomalies will eventually find perfectly satisfactory natural explanations. Or perhaps it is something more. Something that transforms our understanding of the place we occupy in the cosmos. Only time will tell. And in the meantime, we will keep watching, keep measuring, keep asking. Because that is what we human beings do. We look up and we wonder. And sometimes, the answers we find are more extraordinary than we ever could have imagined. Well, my friends, we have reached the end of this journey through the mysteries of 3i Atlas. I hope you have enjoyed this voyage as much as I enjoy telling it to you. Before I say goodbye, I want to ask you something. If this story made you remember some moment in your life, perhaps when you looked at the sky as a child with your parents or grandparents, leave me a comment telling me about it. I would love to know what memories the universe awakens in you. And if you want to continue accompanying me on these starry nights, subscribe to the channel so you do not miss any new cosmic adventure. Felipe Suarez here, wishing you clear skies and interstellar dreams. Until next time, dear listeners.